Question 1 is beyond the scope of year 12 electricity. This is a year 13 question, so we can ignore this one, question 1, and move on to question 2. So it tells us that our cables used to transmit electrical power, with a central core of steel cables surrounded by sheets of cables of low resistivity material, such as aluminium. What is the main purpose of the steel core? And the option it gives us is to force more current into the outer sheath. So if the purpose of the steel core, I beg your pardon, was to force current into the outer sheath, we can think of this just like a normal circuit. Here we've got some sort of supply of potential difference, a cell, and we have a resistor. This represents the sheath, and here we have the core, and we've got the resistance of the sheath is some value, and the resistance of the core is some value, and this is some value V. The current that goes through the sheath will only depend on the resistance of the sheath. So the current is equal to V divided by RS, because the potential difference across both the sheath and the core is the same. So the fact that we've got a core here is not going to change the current through here. So if we added another path with something else, that's not going to change this current. It will change the overall current, but not this current. So it's definitely not this one. The second one says to provide additional current paths through the cables. This is true, but RC is very, very large. It's going to be, we could consider it to be so large that it's effectively infinity compared to the resistivity of the sheath. Therefore, any current that goes through the core is very, very small and makes very, very little difference. So this is not going to be any sort of advantage. To reduce the power loss, well, how is power loss? Power is lost through resistive heating. As the current passes through the sheath, some of the energy is transferred to the ions making up the sheath, which will make it become warmer. But this just depends on the resistivity of the sheath. Having the core in parallel is not going to make any difference. So the only option is D. The steel core is there to increase the strength of the cables. Question 3. Okay, so it tells us that 3 identical cells, each of internal resistance or are connected in series with an external resistor of resistance, or a current in the external resistor is I. If one of the cells is reversed, what is the new current in the external resistor? So let's take a look at what this looks like. So we'll just draw a quick circuit diagram. We have 3 of these cells, and each cell has got an internal resistance, or let's say the EMF of those cells is V, and we've got an external resistance, or the current going through that is I. Now we can just reorder these things and redraw this like this. So the 3 cells together in the same direction gives me a voltage of 3V. I've got my 3R resistance from the 3 internal resistances and the external resistance. So I is equal to V divided by R. So the current is 3V divided by 4R. And what they say is that one of the cells is reversed. So if I reverse one of the cells, what I'm saying is it's not going to make any difference to the internal resistance. I've still got 3 of those. I've still got my external resistor. But now this one is in the opposite direction to this one. So if this was plus V here and 0 here, this means that this will end up being 0 here, because it's in the opposite direction. These two cancel out. So if they cancel out, what I'm left with is the same amount of resistance, but now I've only got V instead of 3V. So this time the current is going to be V divided by 4R. That's the new current. Therefore, I dash is equal to I divided by 3. So the answer is A. So the thing you need to practice is remembering how do we add up cells when they're in series or parallel. How do we deal with resistors in a series circuit? We just add them together. Question 4. In a cathode ray tube, this is an electron gun that accelerates electrons. We've got 7.5 by 10 to 15 electrons hitting the screen in 40 seconds. What current does this represent? And we're told the charge. So we're told that the number of electrons, I just read that, is equal to 7.5 by 10 to the 15 electrons. And the charge per electron is 1.6 by 10 to the minus 19 coulombs. Obviously it's minus for electrons, which means the total charge is 7.5 by 10 to the 15 multiplied by minus 1.6 by 10 to the minus 19. 7.5, 15 multiplied by 1.6, 19, which gives me a charge of 1.2 by 10 to the minus 3. Now the sign in the charge, all this is really for is telling us what direction would these particles be accelerated by an electric field, for example, from a cell. In other words, they'll be attracted to the positive side of the cell. So we don't have to worry about the sign, we're just thinking about the magnitude. So this is the amount of charge we've got. The time is 40 seconds. Get our equation sheet. Electricity. What equation do we have with charge and time and current? It's this one, so that current is equal to the change in charge over the time taken. So that's going to be 1.2 by 10 to the minus 3 divided by 40 seconds. So my current is going to be 3.0 by 10 to the minus 5 amps. Answer C. Question 5. So in question 5, we're told we've got a cylindrical conductor of length L, diameter D, resistivity P, resistance R. What is the resistance of another cylindrical conductor of length L, diameter D over 2, and resistivity? So the resistivity is the same, the length is the same. The only thing that changes is the diameter. Okay, so we have to remember that if we look at how resistivity relates to resistance, we've got resistivity is equal to resistance multiplied by area divided by length, which gives us that resistance is equal to resistivity multiplied by length divided by area. The length stays the same, the resistivity stays the same. The only thing that's going to change is the area, and the area is going to change because the diameter has changed. Therefore, R depends on 1 over area, which means that R depends on 1 over the diameter squared, because it's a cylindrical conductor, and that area, the cross-section area, is pi r squared, or pi times diameter over 2 squared. So the resistance depends on 1 over the diameter squared. Therefore, if the diameter is halved, the resistance is 4 times. Answer B. Question 6. A cell in a circuit has an EMF of 2 volts when a variable resistor has a resistance of 4 ohms. The potential difference across the terminals of the cell is 1 volt. What is the PD across the terminals of the cell when the resistance is this? Now, what this is telling you is because the voltage across the cell is changing, that's telling us that what we've actually got is we have a circuit that looks like this. This is our external resistance. This is our internal resistance that we can't see. And we have the voltage there, the EMF. And we're measuring the voltage from this point to this point. So we're measuring the voltage across this resistor. So that's going to be depending on the current. So the voltage that we'll measure is equal to whatever current we've got times R. The current, because this is a series circuit, is the voltage divided by little r plus big R. So what we're told that the EMF is 2, so we know that already. This is equal to 2 volts. And we're told when R is 4 ohms, then the voltage is 1 volt. So we have the voltage across the resistor, let's call this the EMF rather than V. So the voltage across the resistor is equal to, and we've got the EMF times external resistance over the internal resistance plus R. Okay, so let's put in some numbers. So first of all, we had when the voltage was 1, it was equal to 2 times 4 divided by little r plus 4. So that gives me that R is equal to 4, gives me R is equal to 4 ohms. Again, using this equation now, I'm going to look at what happens when big R is 12. So now I've got that the voltage is equal to, it's 2 volt, the EMF is 2 volts times 12 divided by 4 plus 12, which is equal to 24 over 16, which is 3 over 2, but we never write it like that, so all is 1.5 volts. So question 6, the answer is D. Now, the thing is that the internal resistance circuit is actually just a series circuit with 2 resistances. The equation is given to you in your equation sheet, but you can also analyze it just as a. Okay, so this question, it says, which graph shows how the resistance per unit length or of a wire varies with the diameter of the wire? So we're going to be using this equation for resistivity that tells us that resistance is equal to the resistivity times the length divided by the area. And that means that the resistance per unit length, which is R over L, is equal to resistivity over area. So when we're trying to put this in terms of a graph, what we're really looking at is how does this variable R depend on the diameter? Well, we can assume that a wire is cylindrical, which means that R is equal to the resistivity over pi times the diameter over 2 squared. So that gives me R is equal to resistivity over pi times over 4 pi, I should say, over the diameter squared. So that means that the resistance per unit length, I should say, is proportional to 1 over d squared. So I'm looking for a graph that shows me this relationship. So if we look at these, this first one, this is a direct relationship. This is saying that R is proportional to D. This one, this is saying that as D increases, R decreases. So we've got, so this is also a straight line, but the gradient is negative. So this is going to be in the form y equals minus mx plus c. So R again is proportional to D. This is a graph that shows an increase in R with diameter, but this increase is sloped in this way. This could be something like, so this third one, it might be something like span on the square root with diameter. And this is the one that we're looking for, the inverse relationship. So the answer, the one that's most representative of this proportionality would be D. Question 9. In the circuit shown, the cell has negligible internal resistance. Okay. What happens to the reading of both meters when the resistance of R is decreased? So some voltage V, current going through here, we've got two resistances here, and they've drawn this in a way to try and confuse you. You have to remember that in an ideal voltmeter, there's effectively infinite resistance across here. So I'm going to redraw this like this. I'm going to ignore the position of the meters for a moment. So this is more typically how we might draw it. So what's going to happen when this is decreased? Well, if R decreases, then the total resistance decreases, therefore the current will increase. So we expect this to be an increase option, so it's going to be either A or B. So it's not this and it's not this. So now I need to think about what happens to the voltage as this decreases. Well, remember that this is going to decrease in comparison with this one. So if you imagine if I had something that was 3 volts and I had both of these, or 2 ohm resistance, then each of these would get 1.5 volts. But if I change this, so this is now 1 volt and 2 volts, this one's going to get less voltage because more of the energy is going to be transferred to volts, ohms. More of the energy is going to be transferred to this resistance, and we can check that out. So in this case we had V equals I times R, so I is equal to V over R. So in this case we had the current was 3 divided by 4, 7.5, and so then the voltage across this one is equal to 0.75 times 2 equals 1.5 volts. In this case our current is equal to 3 volts again, but this time divided by 3 ohms. Total resistance has decreased, so the current has increased to 1 amp. Now the voltage across this one is 1. Now the resistance is only 1, so that gives me 1 volt. So the voltage will decrease. Answer B. Question 10. In the circuit shown, V is a voltmeter with very high resistance. We've got an internal resistance, it's equal to the external resistance. Which of the following is not equal to the EMF of the cell? So the first option is to say the reading of the voltmeter when the switch is open. When the switch is open, there is no current. Now, no current flowing means that there is no voltage drop across this resistance. Therefore, the voltage drop across a small internal resistance is 0, which means that this voltage must be the same as the EMF. And remember, we're saying is not equal to the EMF, so it's not that one. Here we have the second one, which says the chemical energy changes to electrical energy when unit charge passes through the cell. Well, that's the definition of the EMF, so that is equal to the EMF, so that's not the answer we want. Then when the switch is closed, twice the reading of the voltmeter. Well, what have we got? Well, what we're saying there is we're going to have a certain amount of EMF, and I've got an internal resistor R and an external resistor, which is also R, and then the voltage is across this resistor. It's from this point to this point. To this point. Okay, so now what I can do is I say use my usual equation. The current that will flow in there is equal to the EMF divided by the total resistance, which is 2R, and the resistance of this one is then going to be given by V equals I times R, EMF divided by 2R multiplied by R, so that's the EMF divided by 2. So which is not equal to the EMF, twice the reading. Well, the EMF is twice the reading, so that's not the one we want. And then finally we've got the electrical energy produced when unit current not charge, passes through the cell. Well, it's not current, it's unit charge, so this is not true, so this is the one we want. Question 11. Electric motor of input power 100 watts raises a mass of 10 kilograms vertically at a steady speed. What is the efficiency of the system? So efficiency is equal to the useful power out divided by total power in. And we've got the total power in, which is 100 watts. We don't have the useful power out, so that's what we're going to need. So we need to have something that links the power, useful power, and we've got a mass and a speed. Well, we know that, and it's given to us in the equation sheet, that work done equals force times distance, but also moreover, power is equal to force times velocity. So power is equal to force times velocity. What's the force? Well, the force is going to be equal to the weight. So that means the power is equal to 10 multiplied by 9.81 times the speed, which is 0.5, which gives us useful power has got a value of 49.05 watts. So the efficiency is equal to 49.5 divided by 100, and the answers are given in percentage, so we multiply it by 100 to get it as a percentage, which gives us an answer of 49%. And the only one of those that's close to that answer is C, rounded to 50. Question 12, we don't do. This is year 13, so we can ignore that one. Question 13. In parts 1 and 2, circle the letter corresponds to the correct answer. The resistance of a negative temperature coefficient thermistor. So